Hi, my name is Ameen Ali, and I will present this work, which is a joint work with Idan Schwartz and Tamir Hazan from the Technion and Lior Wolf from Tel Aviv University. As a motivation for our approach, previous works on video and text retrieval attempt to learn a shared embedding space statically, meaning that the representation of the video is independent on the representation of the text, and the same thing for the other direction. We, however, propose to learn a shared embedding space with conditioning the first modality on the second modality, and the same way for the other direction. For example, given the following sentence, we condition the representation to highlight the relevant frames, which are marked with red borders, and we can see that the high scored words are very related to the chosen frames. This is a high-level view of our model. As you can see, given the frame representations and the word representations, we condition them by a dotted product to get scores, which are later converted to probability distribution in order to recalculate the conditioned representations. Our conditioning unit is based on dot product. In this example, we can see that the interaction between the first frame and the word woman gives a score of 0.4. We do the same for all of the frames and all of the words to get a scores matrix. In order to calculate the conditioned representations for the frames, we calculate the different frames scores by summing across the words interactions. And the same thing applies for the other direction. This is a mathematical illustration of the previous slides. After we get the scores, we transfer them into probability distribution and calculate the weighted sum to get the conditioned representations of the different modalities. In the settings of video and paragraph retrieval, each video is composed of multiple clips, and each clip has a corresponding sentence describing it. In order to apply our previous model on the paragraph and video retrieval settings, we add the following unit above our previous model, which contains two GRUs, one for the clips and one for the different sentences, and we later max pool across all of the segments to get a global video and paragraph representations. Both GRUs are initialized with the global representations of the video and the paragraph. The loss we employ is based on the marginal loss and is applied over the clips and sentences. M is a learnable matching score, which takes a clip and sentence representations and returns a score. The first term is applied over the pairs of clips and sentences in the same video, and the second term is applied over the pairs in the patch. This is the definition of the matching operator. U and V are learnable matrices. The loss of the task of video and paragraph retrieval adds a new term, which is based on the marginal loss over the global video and paragraph representations, for the goal of minimizing the distance between the matching pairs and increasing the distance between the unmatching ones. One limitation of our approach is that it requires recomputing the representations for each candidate match, which increases the time complexity. To solve this problem, we use a static approach to calculate a short list of a fixed size, and later applying our model over the new list. As can be seen in the graph, we report the retrieval performance for each short list size. Results for video and sentence retrieval are shown in the following table. For datasets containing multiple sentences, we concatenate the sentences into one sentence. Our method uses only the text data and video data, and still we show better performance across the datasets. These are the results for video and paragraph retrieval. In these settings, we also employ the clips annotations, and we also show better performance across the datasets as well. We also conducted ablation studies to our model, and as can be seen, conditioning the different modalities really improves the models compared to the static approaches. In the settings of weakly supervised video retrieval, we replaced the current truth events in the ActivityNet datasets with equal length, non-overlapping temporal segments. N denotes the number of segments to use. We also try our approach on other tasks like video-guided machine translation. The goal of this task is to translate a sentence from the source language to a target language given a relevant video to the sentence. One more benefit of our model is giving explainability. Moreover, we also show qualitative results of our model, and we can see that the most of the low score frames tend to be splash screens or logos. Thank you for the listening. We would love to see you with our poster.